let's start again. So the second, I don't know, 3/4 of this is about the proof of the semistable reduction theorem. So we've seen the statement, now I'm going to do the proof. As we sort of mentioned before, you can prove for curves or you can prove for abelian varieties. We sort of said rude things about the proof for curves, so implicitly we like the proof for abelian varieties. So let's do that proof. So I want to simplify things a little bit. So now I'm going to assume that S is a discrete valuation ring, or the spectrum of a discrete valuation ring, a tree, and it has K as a fraction field, and A over K is an abelian scheme, abelian variety, whatever, and what else? Well, the residue characteristic of S should be P, which may be 0 or may not be 0. And I'm going to have L at prime not equal to P. So a lot of the things I say will also work in the case where L is equal to P, but things get more complicated, and I also don't need them, so I'm going to not do them. I'm going to choose a separable closure Ks of K, and I'm going to write Gk to the Galois group of Ks over K. So I want to talk about what do I want to talk about? The Tate module. Everyone's seen the Tate module, so let's quickly define it. Tate module. This is this T L A, which is we're going to define as the limit over what? Limit of A of K S of L to the N. Limit of the N is the limit of the colimit, or the transition maps are given by multiplication by L. Okay? This is the GK module, L module. And well, as a module, it's isomorphic. So Z mod LZ, but 2 dimensions of A. As a Galois module, it's, well, more interesting. Okay, so I'm sort of blasting through this because I think everyone's seen this at least for elliptic curves. If you're not happy, then please complain. I will try to make you happy. So inertia. So we have an inertia subgroup of GK. So there's a couple of ways to think about this. So we've chosen a separable closure of KS. So S prime is going to be the usual closure of, say, S in K S, and we're going to choose a prime of S prime over, oh, it doesn't have a close point. We little s, S. And then I have a couple of ways to define the inertial subgroup. So one of them is to say that I have a map. Sorry, slow down for a moment. So the closed point of capital S, we're going to call little s, and we want to name it the residue field. And if I try to write little k, then they will be illegible. I mean, you won't tell the difference from big k and little k, so I'm going to call it F for the residue field. It's not necessarily a finite field, but it could be. Okay, so here's my F. Okay, so here I have, and so I've made the choice for prime, and so this gives me a choice. So the residue field of this thing gives me a choice of a separable closure.
Algebraic closure.
Sure, but I can take the separable closure inside. But yes, but indeed, like maybe it would be better to say it naturally gives a choice of algebraic closure, but I can do
the residue field of S prime, right? That is the algebraic closure.
Yeah, so the residue field of S prime is the algebraic closure of F, and then I can take the separable closure of F inside. Awesome. So please interrupt in this section because I always get this, I always make a mess of this. So I will try not to make a mess of it today. We'll see if I succeed.
So can I just ask, by a prime of S prime, do you just mean a point of S prime?
Point.
Sorry, yeah, closed point, a point lying over.
Yeah.
So is S a DVR or is it the spectrum of a DVR?
True. It's a deep philosophical point. Okay, so we've chosen this thing. Okay, so we know that, what do we have? Well, we have a reduction map, right? So, we get our map from GK, goes by reduction to G, sorry, not G or F, and the inertia is the kernel.
There's a decomposition group.
But I thought I was, oh, have I made a mess here?
What is this S now that you do? Big or small?
Sorry, this is my big S.
Yeah, but
No, isn't this okay? Define the covers of.
no, I
What
think
about
if it is
this?
Sensiblean also maybe, but if you go to complete, I mean,
I'm mixing up the Henselian and the non-Henselian version here, I think.
Yeah.
Good. Yeah. So, you're completely right. I am indeed managing to make a mess of it again, I'm sorry. So, if I write Henselian here, then I'm like. Then this becomes true, and I don't have to take a decomposition route, so things are okay. Do you agree with this?
I agree with that. That also then there is exactly one point in the above little s in S prime.
Okay,
right?
so my choice was an easy choice to make.
Yeah. Shouldn't be,
Okay. So,
okay.
yes. So I can also think of the inertia as being the things in here which act trivially, which fix and act trivially, right? So the decompositions are things which fix the prime, but I said in the Henselian case there's only one, and the inertia is the things which, the subgroup of things that more of act trivially on the prime, and so that's this thing here. That's another way to say the same thing. Okay.
In fact, normally this inertia is only defined up to conjugation, right?
Which is the choice of
But
this.
in this case, then this cannot go.
Yeah, so is that
Yeah.
cool? Okay. So as a little bit of motivation, we have the known Obshav-Radich, which is that A over K has good reduction if and only if I act trivially on T A. So the reason I'm mentioning, so this was, we already kind of already discussed this in the very first lecture, so I won't spend too much time on this, but what I want to remind you of this. So we're going to understand when A has semi-stable reduction in terms of the action of inertia on the Tate module. And so somehow it's not completely weird that this can happen because we already know that having good reduction says the inertia acts trivial. So generally inertia action should tell us about what the reduction looks like. So that's not so strange. So C Tate. Good reductions will be in varieties. Okay. So what's the, so I want to replace good by semi-abelian. So what do I have to replace this part by? So inertia is no longer going to act trivially in general, but it's going to have a very nice action. So I'm going to make a definition. So we say the action of I on T A is unipotent of rank 2. Unipotent. Sorry, of rank 2. So there's, if say I act trivially on TL A modulo. Okay, so this is the inertia invariance of the Tate module, so the things which are fixed by inertia. This gives me a submodule, so I can quotientify this submodule. And moreover, the inertia action still makes sense on this quotient. And so I always have an action of inertia. The quotient always makes sense, and there's always an action of inertia. And the requirement then is that the action of inertia on this quotient should be trivial. So certainly if I act trivially on TLA, then this is equal to TLA, so the whole thing is 0, so I act trivially on it. So I act on trivially is a special case of this unipotent of rank 2 thing, but this is a more general thing. You can also just phrase this in terms of the existence of a submodule which is on which inertia acts trivially and such that inertia acts trivially on the quotient, but it's equivalent to this. And this
It's
is
also being the extension of two unramified ones, right? That's what you have, because the quotient is unramified and the sub is
Oh,
unramified.
nice. Yes. So being unramified in the sense of inertia trivially, so this unipotent of rank 2 is the same as being an extension of two things on which, such that inertia is trivially on both. Okay.
Are you saying that the inertia group takes any element in the tape molecule to another power to a fixed, or just like what was it?
No. I mean, because it's an action, so like, it must, like every element of the tape module must have by ejection, but it hasn't been like.
If you
Right.
subtract the identity,
Right.
then
So equivalent being. Actually, I'm not completely sure about this, but.
yeah.
So I have to, this implication is quite easy. This implication I found more confusing, but actually you said that this was,
Yeah.
you told me how to do this and I forgot. So apparently this is still, this is very elementary. This we should ask you. And he will remind us how to prove it. So this is we won't use this at any point, but it's just, I don't know, it gives a more sort of concrete way to think about this. So the analog of neuron Shafarevich, this is called the Galois criterion for semistable reduction. Says that it's just the analog of this, so A over K has semistable reduction. If and only if I, right, how do I write this? Action of I on TLA is unipotent of rank 2. Of course, the left-hand side doesn't depend on the choice of I, and a priori the right-hand side does depend on the choice of I. But well, by the truth of the theorem, we know that it doesn't depend on the choice of I. Have I said something you've got trouble with? Everything in the
No, but I think the arrow should not be that difficult.
which arrows?
Right to left.
I think you're, I think you're,
Oh, yeah.
yeah.
Can I just ask about the terminology? So the rank 2, is that because it's like a rank 2 CL module or because?
Sorry, it's because it's an extension of
Two of two trivial
Yes,
things, the other.
yeah, sorry, so it has nothing to do with the rank as the rank is the
No,
one
no,
of those two.
that was exactly. the
Yeah,
question.
that's a very good point.
Yeah, and then the thing about is probably called unipotent of rank 1. If you act trivially.
Well, yeah.
That seems good.
Yeah, no, okay,
Yeah,
I was just wondering.
Yeah, because that's the same, I mean, the 2 is this 2, right?
Yeah.
You put the rank
Sure.
1 says, yeah.
Yeah, sure.
Good.
So I think that you can say that the action of I factors by a quotient that is isomorphic to ZL, so topologically generated by one element, sigma.
Okay, and then
you
you
replace it because
yeah, I mean, if the inertia is like generated or topology generated by one thing, then this implication is easy. But okay, we should use the action factors via, yes, by this tame Avianda's level thing.
but that's because the action is important, I think.
Of some, sorry,
If the action is unipotent of I on the discrete model, then it factors via this the biggest probable quotient of
Yeah.
I
And
think.
then you use that L is not P, so then it is pro-cyclic. Yeah.
okay.
So you have only one sigma to care about,
Yeah.
a generator.
But that seems to be saying if we're unipotent and this holds, then we're unipotent of rank 2, which
No.
is, no?
I think you first use the structure of the Galois group.
Okay,
You say, well, if any sigma in I has to act in this way, then the wild inertia group acts trivially anyway, because it acts through a pro-L quotient, that's what Julio says.
right.
And then you use it that is cyclic, and then
Okay,
you see that you use it for sigma, that is a topological generator, right? And then you take the kernel and the image of that, and you get your sub.
yeah. Awesome. Okay, thank you very much. So, it's now makes more sense. Alright, yeah, so I decided I wouldn't talk about what the inertia actually looked like, and now I somehow find that this is why this was hard. Okay, so we have the Galois criterion for semistable reduction. which is going to help us. So the way we're going to prove the semistable reduction theorem is by, so the semistable reduction theorem says that eventually this happens, so eventually after Taylor field extensions, what we're going to prove is that eventually this happens, which of course will do the job. So, the growth monotony theorem is exactly saying that eventually the right hand side happens. So let me write this down more formally. So actually, well, I'll state the thing. So we also have the theorem with leaps. I'll add it. Monotony theorem, which says that there exists k prime over k finite Galois extension such that the action of inertia of g k prime on T A is unipolar differential. Okay, so clearly if we combine both of these theorems, then we've proven the semistable reduction theorem, so that's very nice. So what, here is another point where perhaps you'll have to help me. So Raymond in his notes actually just proves this. So eventually this thing becomes unipotent of some rank. But obviously for what we do here, we want that it's unipotent of rank 2. So in SGA section, the same SGA 2, expose 9, in section 3 they really prove this in precisely this form. But sort of because Raymond already talked about, I mean the proof of this is, it's very nice, but it's somehow, I don't know, it's not a thing which I relish trying to write on the board.
Does it use curves to get the rank 2?
I didn't think so, but I'm not sure. That's a good question.
Because it's true for the H1, right, of the Nebulae variety, the state
Yes.
module, but it's not true for higher cohomology. Because if you take tensor products of
Then it will
rank 2
multiply.
things, they get higher rank.
Yes. So that suggests.
So something special has to be
Something
used.
special. Yes, that's. Thank you. That's a very good. So, but on the basis that this was sort of preached in the previous talk, and it's somewhat painful to write on the board, I want to focus a bit more on the right-hand side, the Galois criterion for semistable reduction. So why is the action of inertia being unipotent of rank 2? Why does that have anything to do with semistable reduction? I mean, the theorem of Narod-Shafrovich sort of makes this kind of plausible. But let's see if we can be a bit more precise. So I will just sort of, to get the disappointment over with, I'm not going to be able to actually give the proof. Even though I'm going to take more time than I should, I'm still not going to take that much time. What I'll try to do is, so I'm going to talk about various ways to decompose the tape module, and I'm going to talk about the orthogonality theorem, and I'm going to explain. So I'm basically going to state a thing called the orthogonality theorem, give careful definitions of all the things in it, and then explain why the orthogonality theorem implies, sort of gives us this thing, but I'm afraid I'm not going to tell you how to prove the orthogonality theorem. So I'm sorry in advance. Okay, so now I was assuming that my S was Henselian. Let me simplify things further. From now on, S is going to be strictly Henselian, or strictly local, some people say. So in other words, it's Henselian plus the residue field is separately closed. This is not essential, it just simplifies things a bit. Okay. So now I'm going to talk about the toric and fixed parts of the tape module. So here we have N is the Narod model of A over X, and N0 equals identity component, and well is N0F, which is the identity component of the specify that. Okay, so TLN0 is it's just defined in the way you sort of expect. Sorry, that should not be. Yeah, that works. Well, this is. So this is. So how do we think about this thing? So this n0 is a group scheme over the whole of S, and then I can look at the L to the n torsion, and I can take the S points. But this is just going to be the same as the limit over n of by the normal property.
And the fact that L torsion, L to the n torsion is always a tau.
Yes,
Right.
indeed. So thank you. So
No matter what your group scheme is.
yeah,
Commutative, that's important.
yes. Yeah. So we took the point was that L is not equal to P. So the L to the n torsion is a subgroup scheme. So commutativity tells us it's a subgroup scheme, and it has order coprime to P, which tells us that it's étale.
Why the wrong mapping property?
Because otherwise it might not be finite tau, but right? No.
There is injective and surjective, right? So
Yes.
you, I think every unramified. So if you have some, so what is it? No, here you don't use the mapping property because you start with global sections.
Oh, you're right.
So
yes.
you're just using that the restriction is injective because it's unramified, this L torsion.
Yep. And it's
It's
yeah.
étale. It's so the fact that
Yes.
it's étale.
Cool. Indeed. So the answer is not. I will soon.
Yeah.
Okay. So we have a map T L and 0 to T L A. So I think it's clear what the map is. It's just sort of restricted to the generic fiber. Here that gives us some, and the injectivity is indeed here, and right, because these things are just étale, so well, that's going to happen. And the image, so the claim, the image is T the inertia, so I'll put brackets, so because I'm putting subscripts both in and outside the TL part, so this is, so the image of this thing is the inertia index, so in other words, these things are sort of canonically identified. Okay, so I'll see if I can not mess this up. Okay, so inertia acts trivially on the. Okay, so notice that here I put S, and normally we would put some sort of separable closure or a tunnel thing. But this is because I assumed that S was trivially n. Otherwise, morally, I should have put here some sort of trivialization or separable closure. Okay, so notice that I acts trivially on the S points of a group scheme. So we get sort of automatically that this TL of n0 is contained in the inertia invariance. I mean, basically the points of this thing are rational points, and so the Galois is going to act trivially on. So this is sort of the easy direction. So conversely, so let's take okay, so remember the tape module is a limit, so I'm going to take this sort of sequence of things representing the element of the limit. So some xi is a k set point of A fixed by inertia. Of course, it's not just a point of A, it's a point of the L to, say, L to the I torsion of A, which is better. But remember that we had our exact sequence. The inertia is the kernel of the map from the Galois group of big K to the Galois group of F. But the Galois group of F is trivial because of our strictly Henselian assumption. So actually the inertia group in this case is the whole Galois group. So this is indeed, this makes things simpler, but in some sense it also makes things a bit more confusing. So I'm not sure if this is really, I don't know. It's important not to get mixed up here, but anyway. because the inertia is actually, under these assumptions, the whole of the gamma group, this tells us that then xi is actually a k point. The thing is, it's maybe a little bit nicer if you don't, so if we don't assume the strictly Henselian thing, then being fixed by the inertia will tell you that you're unramified, and then you can apply the narrow mapping property to your sort of with a smooth entire test object, and you get that it lives in some entire extension of X. And maybe this is maybe this is something a bit nicer. But anyway, in this case, this is how it all works. So great. So it extends to the narrow model to n. Great. So we get that TLA I is equal to TL of n. Okay, I haven't defined TL of n, but I think you can guess. You just delete the 2 zeros and that gives you a thing called TL of n. And so this is the point that I got to a couple of afternoons ago when I was preparing this talk, and then I was somehow confused because I was like, I want a 0 here. So I went to our studio and he told me how to put a 0 there, so this was great. And so let's see if I can get this correct. So basically the point is that, so remember that what's the difference between n and n0? It's this component group. So the special fly group, so we can also write this as DL of sort of these things are the same. Using the normal method. So this uses the normal mapping property. But again, there's a difference between this NF, sort of there's no 0 here, and the difference is the component group. This is some finite group. But the thing is that
the equality uses the equivalence of categories between finite covers of S and of F.
Yeah.
Not the narrow mapping for
Yes.
Yeah, because you have already S points
So I have
in the TL of n. So you're not using it. You're just restricting to the closed point.
S. So I have S points of TL of n, and then
narrow mapping.
yes, you're right. Yes.
Or
Yeah, you're completely right. I'm sorry. Yeah, I was getting my and my mixed up. Yeah, indeed. So here like we really essentially use the normal. Okay, so again, we don't have our 0, so how do we get our 0? So the point is that this xi, I mean there exists an xi plus 1, and L times xi plus 1 is xi, and you can keep repeating this. So this xi, Joey, this is actually infinitely divisible by L. But note, xi is infinitely divisible by L. And so that then tells you that actually it must live not just in NF but in N0F. So must live in N0F. So to make this maybe a little bit clearer, we have some exact sequences.